Okay. And now?
Yes, now is correct. Thank you. So please just introduce yourself and also start. Can you also start with
Yeah.
presentation?
Yeah.
You.
Thank you. Thank you so much for your time. And so my name is Abdul Wahab Ayari. I'm application engineer working for Mentor since 12 years. I'm supporting customers across Europe in functional verification, in particular in form verification, clock domain crossing, and low power. Today, I will present a paper about how to use form verification to prevent deadlocks. So I will start briefly with the deadlock cases to consider here. Then we will talk through typical approaches used for deadlock analysis and the challenges they are facing. Then we will discuss Mentor's enhanced deadlock solution. I will cover some application for deadlock analysis, and then I will draw conclusion at the end. So deadlock are very critical and difficult to find. We distinguish two types of deadlock. Type A is actually the case when your design reaches a state and cannot leave the state anymore. It is like this icon here in this trap. He will not be able to go out in his own. Type B is actually when your design reaches state and can stay there permanently by avoiding possibility to exceed the state. So this is like the koala here. He is hanging in the tree until he decides to get down for some reason. So let's consider a really trivial example here. For type A, we can see that once in state 3, there is no real way to go out. There is no way to go out from state 3. So if we ignore reset, of course. So this is a true or a real deadlock. If we consider state 2, here we can see we can get stuck on state 2 as long as the select signal cell is left low. So if the signal cell is always low, then we have a true deadlock. If the signal cell can toggle from time to time, then the design can go out from the state 2, and we don't have a deadlock. So actually, type B is kind of potential deadlock. I will call it maybe escapable deadlock. Usually, simulation emulation can mainly discover deadlock of type B. Formal verification can report both types. And actually, in a lot of cases, only type B. So this is the subject of the presentation here, and we'll talk a little bit in details about this. Let's consider first how deadlock analysis is done so far. Simulation is actually the widely used solution for deadlock analysis. Deadlock checkers are often implemented as watchdogs in Verilog in VHDL. Watchdogs are mainly counting how long to stay in a state or how long to wait for an event to happen. As we have seen in the previous presentation, simulation has several weaknesses. I'm listing here 3 of them. First, it is hard to recognize if the design is in deadlock state. So you don't know how long you have to wait to decide that the deadlock is really happening. The second thing is actually it is not easy to distinguish between type A and B. If you think that the deadlock that you are investigating is an escapable deadlock, then you have to prevent or to provide stimuli showing how to exceed that state. Providing such a stimuli is actually very hard. The third weakness is actually a very generic one, is writing stimuli is anyway incomplete, or simulation is anyway incomplete. And this is actually much harder in the scope or in the situation where we are dealing with deadlocks. Things becomes very hard and complex. So bottom line, simulation is incomplete and is as time consuming, is not maybe not the right one to use for deadlocks. Now let's move to formal verification and consider first if safety property can help us. I will demonstrate a common used approach here using this simple FSM. We want to check if this incremental to X state can be a deadlock state. So the idea is very simple and consists of 3 steps. First, a step consists of to find a trace where the FSM can reach the state incremental to X and stay there for n cycles. This is expressed by this directive, by this cover directives. So if the tool provide a trace for this, then we can use this trace as an initialization for the next run. We call it also sequence as initialization sequence for the next run. And in the next run, we will ask the question if we can stay there on this incremental to X state forever. If the tool prove that is okay, that is possible, then we have a deadlock. Otherwise, we have to go back. We don't have a deadlock, then we have to go back and maybe adjust our initialization by modifying this cover directives, adding some signals or changing the delay here. So this is something that it can be used, but it's actually also partial and very time consuming. Now, let's move to liveness property. And I will continue to use the same FSM here. I want to check that this incremental to X state is not a deadlock state. It means I have to prove that at any time there is a time point in the future where the FSM will be not in the state incremental to X. This is expressed with this System Verilog assertion, always as eventually state different from incremental to X. So if I have a proof, it means that every computation path has a loop where the FSM state can be different from the incremental to X. So this means that FSM is always able to exit the incremental to X state, which is nice, and we have no deadlock. In case that this property is violated, then there exists a trace with a loop where the FSM state is all the time in the incremental to X state. And the question here is now, what type of deadlock we have here? Is this type E or type B? So we have to keep in mind that this is a System Verilog assertion, liveness property, and this is what the tool will provide as firing as a counterexample. Now, what it can say is that actually, in this deadlock path, the tool will not check if there is an escape routes. So we have a loop here. The tool will be not checking if there is a way to go out. And any tool which is using this System Verilog assertion semantics. This is because actually of the System Verilog semantics, which is based on paths, does not allow to go after possible branches in the loop and on check for escape routes. So this kind of checks are not mandatory for the tool. The tool will not do it for you. So the tool will actually provide this loop and tell you this is a counterexample. Will not do this kind of checking if it is possible to go out. Actually, this is the koala state that I demonstrated before. Or yeah, you have seen this before. So actually, we can say that liveness property in LTL or System Verilog assertion give maybe escapable deadlocks. I will show you on a simple example the impact of this. this has actually heavily impact, a very bad impact, and I will show you what does it mean. Let's consider go back to our FSM, and I'm asking actually if this incremental 2 is in a deadlock state. The tool is showing me this as a kind of counterexample. This is a deadlock counterexample. We see that there is a loop here in the incremental to x. And actually, I know that this is actually not a deadlock, not a real deadlock scenario. And I have to push the tool to give me a real deadlock state waveform, or to prove that there is no deadlock. So what I have to do is actually what you see here, that in this loop, the data is always 0. And I will ask for some fairness that the data can be also different from 0, and to see if this helps to the tool to move in the right direction. So I will add fairness condition telling that the data is from time to time different from 0, and see what happens. If I do so, the tool will give me the next waveform, telling there is still a loop, still that maybe escapable deadlock. And here what we see is that the data is indeed not 0. It is 2, 3, 3, 2, 3, 3, and so on because of the loop here. And actually, this is still not a deadlock. And I am still asked to help the tool and to add more constraints to help the tool getting the right things. So I will ask the tool actually, because he is looping over 2, 3. I will ask the tool that from time to time I want to see also the data input is 1. So I'm adding this fairness condition. So if I do so, the tool come back again with the next deadlock waveform, and where we see that all the possible values except 0 is actually used. And still, I don't have a real deadlock scenario. So actually, at some point, even in this small example, it is becoming hard to add more constraints to escape this deadlock. It becomes more hard to help the tool to look for real deadlocks, and also make them possible to prove if there is no deadlock. So what we can see is actually that in summary, System Verilog shows maybe escapable deadlocks. User is asked to add constraints to escape the deadlock. Debugging process is very painful. More interestingly, is actually there is a risk to keep real deadlock if user don't succeed to find escape routes. For example, tool will not check other paths and eventually miss real deadlocks. So this is something that is actually not good for liveness property based on the System Verilog semantics. So now we will not give up. Let's look to the next formalism that we can use to achieve our goal. The next one is called computation tree logic. It's in a temporal logic, very familiar or very similar to linear temporal logic. There is a fundamental difference in that this CTL is based on trees and not on paths, which means actually if we find a loop as a candidate, as maybe escapable deadlock, per semantic, the tool is forced to prove if there is escapable routes, if it is possible to go out. So it means actually this is in contrast to LTL, which is there is no condition to do this. So the tool is not asked to do this for LTL, for System Verilog. So LTL or System Verilog are the same. So this is the case for CTL. So CTL will be, there is an obligation for the tool to do so. which actually this is what we are looking for. So it means when the tool is tell us there is a deadlock, then this is real deadlock. So actually CTL looks like that is good candidate. The problem is that actually CTL is too academic for regular engineers. It is not supported too much or not supported at all actually by commercial tools. So if I summarize so far, the approach that we have seen, simulation is incomplete, safety property are incomplete, very time consuming, liveness property are also incomplete and time consuming. CTL could do the job, but actually is not supported. So we need a new actually kind of new approach. And this is what Mentor did. Mentor had added to its Questa prop check formal tool a new unique capability. They combine LTL, CTL semantics for liveness property. LTL is used as before explicitly for writing property. CTL is used implicitly to analyze deadlocks. This approach is actually officialized or officially added to Questa prop check since 2 years. I have to say here, actually enabling this CTL checking in Questa prop check has no impact on the flow. So the way that you are writing assertion, debugging assertion is the same. You are also not required to make any engine orchestrations for the CTL engine. This will be done by the tool itself automatically. The most beneficial stuff is actually the tool that this approach is complete now. So we can get proof, we can get real deadlocks, and we get escapable deadlocks. So this is how to say, this is really a good thing because we get rid of adding fairness constraints and wasting a lot of time. So this a little bit in more details. The flow starts with checking a liveness property with LTL. If it is proven, then we have no deadlock. That's fine. If it is not proven, then it means we have maybe escapable deadlock, and we will use the CTL engine. If the CTL tell us there is a deadlock, then there is indeed a deadlock. Then you have to go back and debug your design, fix the design. Otherwise, the tool will tell us that maybe escapable deadlock reported by the LTL is actually escapable. There is a way to go out. And in this case, actually, it gives you how to go out. It gives you a waveform showing how you can escape the deadlock. And you will see the condition that makes possible to escape the deadlock. And here your task will be to make sure that these conditions are actually legal. It could be the case that, for example, the tool is using the reset to go out from the deadlock, or using some scan paths or DFT stuff or whatever, something which is actually not legal, or changing configuration registers or whatever. You have to see, you get the waveform, and you have to investigate this and decide if this is legal or not. So let's go back to our example. So the last time we were a little bit frustrated using LTL to prove that this state is not a deadlock state. So if we enable deadlock checking in prop check, we get a result, which is a little bit different from what we have seen before. We obtain a waveform telling that there is indeed a deadlock, a real deadlock. There is no escapable. This is a deadlock, and there is no escapable waveform for this. And actually, if you see a little bit here, you can also understand that this is a real deadlock, because the state incremental to 2x can be exited only if the counter is 0. But the counter can never be 0 in this situation because it has the value 3, and we will be incremented by an even number. So this is the condition to exit with counter 0. The counter can be only incremented by an even number, and if it is 3, it will never be 0, and we will stay forever here. So the tool actually using the CTL stuff is helping us too much and saving all this fairness exercise. So let's do one more example and ask the tool if the state increment here, this state here, is a deadlock state. The tool will report here there is a maybe escapable waveform and also a condition to escape it. So the waveform in general is escapable waveform. We see here that you can loop here for some time, but there is a way to escape that by using or forcing the data to be 2. And this means actually that this state is not an increment, it's not a deadlock state, and potentially escapable deadlock provided by the LTL can be escaped, and this is the way how to escape it. And because data n equal to 2 is a legal condition, then this escapable waveform is acceptable, and there is no deadlock. Okay. So as I said, this is in use since 2 years. Some of our customers are using it already. Here is Laurent, is one of the ARM's leading formula experts. This is a quote direct from the DAC, last DAC paper, just confirming that debug is indeed easier with the new solution from PropCheck. Here is some more results described in ARM paper last DAC. I'm not going to discuss all this application in detail and will recommend you to read the paper, which is selected as best paper. We can see that ARM is using this concept to address deadlock of complex FSMs, to check correctness of arbitration, and check deadlock protocols. In all this application, ARM was able to find bugs and report that debugging is actually much efficienter than the old flow. So for more details, as I said before, please take a look in this paper. All right, so some other cases that we see our customers are targeting are interfaces. You have to make sure that the different components in the interface can access, read, and send data. Other applications are handshaking, but I can say in general, any liveness property, this approach is applicable for any SVA liveness property. Because if SVA liveness property has a counterexample, it has a maybe escapable deadlock, can be seen as maybe escapable deadlock, and you have to find out if this is actually a real deadlock or not. And for that, you have to use the CTL semantics. Okay. So in summary, I can say that simulation is not the best approach to explore deadlock in RTL. The risk is too high to miss real deadlock cases. PropCheck provides the most advanced formal techniques to analyze deadlock, and real application showed very promising results using this new feature in PropCheck. So I'm done. Actually, yeah, thank you for your time. Any questions?
So thank you very much. Do you have questions? Maybe we can start with one. Do you double check also the complexity of the design? So do you have any or the complexity of the properties is also can play also some efforts in the verification, or you can also handle this in an easy way?
So yeah, that is one thing. As long as you are handling control stuff, things are actually okay for form verification, and in particular for deadlock. Deadlock is actually very hard check. It's not is actually from the complexity is actually more complex than the other checks, because you have to prove two things: the existence of this loop and the way that to exit it. But what is actually bad for deadlock or for FSMs? If you have FSMs in which you have the transition are guarded by counters, you see, that is we see that this is could be problematic, and a tool can have how to say can run for more time. So because counters, you have to explicitly wait for certain number of cycles, and this can have impact on the deadlock checks. But if your FSMs are actually not necessarily related to counters, they are about more controls, then this is also fine. There is also other ways to deal with counters. You can also put in place some kind of abstracted model and work around this problem. So we have this in use. We have this in use in module-based, which is simple module-based, I have to say. We have this in use in the IP level, but also in certain cases at the SOC level, and so at subsystem level, let's say. And it depends on the complexity, what this design is doing. Sometimes you have to wait a little bit for getting the proofs. But as I said before, if it is actually about controls, the deadlock checks are actually fine and can be also found quickly.
Okay, thank you. Is there any other question? Otherwise, I'd like to thank you again for your talk. And also, I'd like to thank all the attendants and participants here in this session. And I'd like also to invite you all to the next session, the keynote presentation, talk about the future of compute and where the verification also plays a really important role. So thanks again for your attendance, and also have fun today.